We'll be ready to go. All right. Before we get too far along here, let me go over just a few announcements. I think I announced it last time. I think both of you here, but in case you didn't hear, I had eye surgery on last Thursday, okay? And so I was off campus all day Thursday. Okay, so this is my first day back, and they took out my existing lens, which had a cataract growing in it, and put in a fixed lens. You know, your lens, your muscles, help you focus. When they put in the artificial ones, they're fixed. There's no focus to it. So y'all look very clear, but the book doesn't. So I have to wear reading glasses now to read the book, okay? Now you look fuzzy, okay? So I'm going to be back and forth until I get used to how to do these things. But the surgery went really well. What I didn't realize is I would be basically out of any usefulness whatsoever all day Thursday. When we got home from surgery, it was still mid-morning, and we were there at 5:30. I basically slept the rest of the day. I mean, not solidly, but, every time I'd lie down for my wife to put the drops in my eyes, I'd fall asleep again. And I just slept most of the day. She almost woke me up to put the drops in, 5 hours later. Not quite that bad, but pretty close to it. And I couldn't see anything. My eyes were dilated, or this one was dilated, and I was just totally worthless that day. Got zero done. I had hoped to get a little bit of stuff done with all that time off. Friday, my eye was still dilated, still having to put drops in. I'm still putting drops in. And so I wasn't much more good that day. I couldn't really read anything because this lens couldn't let me do it. I didn't have reading glasses then. So Friday was almost a wasted day. It was nice to rest, but could do almost nothing. But then I think late Friday we went to, seems like that's when we went to CVS and picked up the reading glasses. So later on Friday I had, no, that's right. We didn't go, it was Saturday. But my wife found some old pair of reading glasses of hers, which allowed me to read. They weren't the right size, thing, but I at least could read some of them. But I didn't get much done that day either. I was still dilated. Finally, by Friday night, the dilation had gone down finally. And then Saturday, we had a more normal day. But I still am not supposed to lift 10 pounds, and I'm still not supposed to bend over because of the eye. So the surgery on the eye. So it's been pretty much a useless time. So I'm not up to the normal stamina that I normally would have because I've done nothing for 4 solid days almost. So anyway, things are better now, and I can see a lot more clearly than I could, but I don't have any adjustments, so I have to be swapping out glasses and things like this to read. But I'll get used to that. Let's see. Also, my follow-up appointment is tomorrow afternoon. It's 2:10, but I'll be leaving well before 2:10 to go to it. The good news is it's right across the street here at UAB West. That's where he is on Tuesday afternoons. So I'll be going right across there, have my follow-up. I don't know how long that's going to take. I don't know if they're going to dilate the eye and do all that kind of stuff, or he's just going to look at it and say, hey, it's looking good, and let me go. So it could be fairly short. It could be an hour or more, okay? So figure I'll be out of pocket probably a little before 3 until a little before 2 until a little probably after 3. About an hour or maybe a little bit more sometime tomorrow afternoon between 2 and 3-ish. Okay. Okay. Another thing that came up over the weekend when I finally could start reading emails, this was Saturday and Sunday, mostly Sunday, I found out I had a report to do in today, so I went on and did it yesterday. and it was what they call the no-show report. Anyone who had paid for the class but had not shown up. Well, no one in this class fit that category. There are a few people who haven't shown up, but they hadn't paid for the class, so that wasn't an issue. However, there were a few people that had not been attending very much, so I put those down as not attending, but they weren't no-shows. Now, the only reason I'm saying that is that it doesn't really affect any of you, and it has nothing to do with this either. It seems like it would, but it doesn't. They also, at some point, are going to remove students who haven't paid, even though they may be coming to class. So they remove students who have paid but have not come to class. They're doing that with what I turned in yesterday. They'll do it over the next week or so. But then at some point, they'll also remove students who haven't paid, even though those students may be coming. So the point of saying this is, I think I said it last week too, please get your payment caught up or completed or at least made in progress so that if they do come to that, at least the business office will know that that's in the works. So do whatever it takes to stay in the course, especially since y'all are coming to class. I don't know, I haven't checked to see who's paid and who's not, but it seems like most of you have. All right. I think that's all of those. Any questions on what we've done so far? Okay, where we left off last time was chapter 12, and I actually gave you the test on chapter 12, that we didn't quite finish the chapter. We're in chapter 12 is vector value functions, and 12.5 arc length and curvature, and we had done example 5, find the curvature of that problem. So that's been done, and we did finish it, I think. Did we go over it here on the slide set? I can't recall. Did we? We did, okay. Because my mark's at the top of the next page, so I thought we had. And that was example 5. Still example 5. Okay. And there's a curvature. Yeah, I remember doing all that. All right, and here is the theorem that describes curvature. Curvature in rectangular coordinates. If C is the graph of a twice differentiable function given by y is equal to f of x, then the curvature K at any point xy is given by this. Now this is a different formula from the one we were just using. The magnitude, y is a scalar function, not a vector function. I don't even show the vector function on here. Y is a scalar function, so if you take the second derivative of y, okay, and plug in a value for x, it's either going to be a positive or negative value. Whatever that is, take the absolute value of that. The absolute value of y double prime divided by 1 plus y prime squared. We've seen that before. Okay, raised to the 3/2 power, and we sort of saw that in the last example we were doing. Okay, and that then is your curvature. This always positive, because y prime, whether it's positive or negative, you're squaring it, that's going to be positive. Adding 1 to it makes it positive, more positive, and then taking a square root and cubing that will be positive. So the denominator is always positive. You take the absolute value of the second derivative at whatever value you're doing, and that gives you a positive value. And Davis is here. All right. Now, I think I messed up something here. Just recalled it. I had one person who emailed me, and I wanted to make sure I noted that email. That's what I'm doing now. Oh, I think I've got it. No, there was one more. I don't see it now. I know it's in here somewhere. But I can't find it. I'll worry about that later. Oh. Okay. Rachel, hi.
Jasmine.
Jasmine, sorry, I knew that. I think that's what it was. Okay. I'll worry with that later. Okay. So that's a new and different formula from the one we did before. And let's just go back real quickly and review what we did before. What we did before was this. Okay? It's taking the function, taking a derivative, taking the second derivative, doing a cross product, the magnitude of that divided by the magnitude of the first derivative cubed. Now, when I said you'd seen the 3 halves before, remember this magnitude here cubed? Well, the magnitude is the square root of the function value, and then so that's where your 3 halves comes from. This is if you're given the function r of t, the vector valued function r of t. That's the curvature formula here. How that differs here, here, can't talk, I'll get there in a second, is this is curvature in rectangular coordinates. If c is the graph of a twice differentiable function given by y is equal to f of x, this is in a plane. The other could have been in a plane or in space. This is in a plane, and the function, there's no vector function that mentioned here. It's just a twice differentiable function. This is how you do the curvature of that. So it's somewhat similar, but certainly not the same. Okay? Now, let C be the curve with the curvature K that we just did at some point P. The circle that passes through that same point P with a radius 1 over K. And I don't know if you remember back a couple of examples ago, we said if you had a circle, its curvature is always 1 over R. So K defines some circle, R defines some circle, and they're related this way. So if it passes through a point, and at that point there is a circle you can draw in there who has that radius, 1 over K, that's called the circle of curvature. The circle passing through this point with a radius of 1 over K, that is a circle of curvature. When the circle lies on the concave side of the curve and shares a common tangent line with the curve at point P. The radius of the circle is called the radius of curvature. That's that R right there. And the center of the circle is called the center of curvature. Okay? Now, the circle of curvature gives you a nice way to estimate the curvature K at a point P on a curve graphically. Okay? Using a compass, if you had a compass, you can sketch a circle that lies on the concave side of the curve at point P and try to get that point P here on this curve here, and I drew one that really fits nicely, and try to get as much of that circle inside of that curve and touching as much of the curve as possible. Do this manually and then whatever radius you have there, that's going to be 1 over that is going to be the approximation of the curvature of that curve, even though that's not the circle. Okay? If the circle has a radius of r, then you can estimate the curvature of the function to be 1 over that r. Okay? That's how you do a manual sketching of this. Okay, here's example 6. Find the curvature of the parabola given by y is equal to x minus 1/4 x squared at x equal 2. Okay? And then it says sketch the circle of curvature at 2, 1. Well, before I do anything else, I want to make sure 2, 1 is indeed on that parabola. So if you put 2 for x, that would be y is equal to 2 minus 1/4 of 2 squared. 1/4 of 2 squared is 4. 1/4 of 4 is 1. 2 minus 1 is 1. So sure enough, that point is on the curve. Okay? So find the curvature of the parabola given by that equation at x equal 2. Now from our formula, let's go back a couple slides. There's the formula. What are a couple things we're going to have to do before we can calculate that curvature? What we're looking for here is our capital K. Now in most other texts that I've taught from, they give it a capital kappa. This one just calls it capital K. In fact, some textbook uses little kappa for curvature. Whatever you call it, that's what it is. So what's the formula for it? The magnitude of y double prime over 1 plus y prime squared to the 3/2 power. Magnitude of y double prime, okay, squared, wasn't it? No, magnitude of y double prime, okay, over 1 plus y prime squared to the 3/2 power. Okay, let's make sure we got it right. Y double prime, the magnitude of y double prime over 1 plus y prime squared to the 3/2 power. Now they put brackets here rather than parentheses, so let me do the same thing. Okay, here's our function y, so what two things have we got to do first? Help me. Take a derivative, always a good answer. In a calculus class, take a derivative. And what would that be? 1 minus 1/2 x. And then we also need y double prime, so let's go on and get that while we're here. And what would that be? Negative 1/2. But we're interested in the absolute value of that y double prime, so that will be what? 1/2. All right. So let's plug and chug away here. Your curvature, that's what they're asking for. Find the curvature of the parabola. And that would be 1/2 is your numerator. Your denominator is 1 plus and y double prime, y prime squared. Well, here's y prime. Y prime squared is going to be 1. Okay. Time out for just a moment. We don't need it for every value, just for that one value. So why don't we just go on and plug in the 2 for the x and see what y prime is at that point, and then we'll just square that. So rather than messing around with the generic form, let's just go on and plug in. So I think what I'll do, y prime at the point 2, 1 would be what? There's your y prime. What is y prime at 2, 1? What would it be? It's 1 minus 1/2 x at the point 2, 1, where x is 2. It would be 1/2 of 1 minus 1/2 of 2, which would be 1 minus 1. This will be 0. So that was pretty easy. So 1 plus 0 to the 3/2 power. Well, what's that? That's 1, so this is just going to be 1/2. Your curvature is 1/2. Because that denominator turns out being 1. Okay? It says find the curvature of the parabola given by that at x equal 2. We did it. It says sketch the circle of curvature at 2, 1. Now my sketches are not going to be very pretty. I think I'll sketch it up here because I see 0, 0 is there, and when x is equal to, and we know that, ooh, I went too far probably. Let me come down with it a little ways. Okay. Do it right here. So 0, 0 is on the curve, and we know that 1, 2, 1. This is on the curve. 2, 1 is on the curve. And we could plug in a few other values if you wanted to. At 1, that would be 3/4. Right about there. At 2, that's probably not quite high enough. At 2, I think we already determined that would. Okay. 2 squared is 4, yeah, 1, yeah. 2 is 0. Wait. No, 2 is 1. We already determined that one. At 3, that would be 3 minus 9/4. 9/4 is a little more than 2, 2 1/4, and 3 minus that, I think it's 3/4 again. No. Let's see, at 4, 4 minus, yeah, 4, 0, yeah. So here is the, this is just approximate, the parabola. Okay, something like that. And at the point 2, 1, we want the the circle of curvature. Okay? Well, if k is 1 at the circle of curvature, what is the radius of that circle of curvature? Anyone know? It's 1 over k, which is 1 over 1/2. What's that? Come on, folks. You know your fractions? 1 over 1/2 is 2. So this has a radius of 2. So for the radius of 2, then its center is going to be right here. And it would be going to here and to here. And so 2 more down to here. So here would be the circle of curvature. I don't draw very good circles, obviously, okay? but that would be the circle of curvature for that at that point. Okay? So, I think we've just done it, everything they asked for. Let's watch them do it. I think it'll be a little prettier. Okay? This is Ashley, right? I mean, goodness gracious, I'm in the other class. Rachel, right? Yeah. Okay, good deal. Now, the radius, the curvature at x equal 2 would be, what you have to do is take the first derivative, 1 minus 1/2 x, that's what we got. Y double prime? No. Okay, at x equal 2, that would be 0. I wish they would have put y prime at x equal 2 or at 2, 1 or something like that. That's a little confusing to put it there. Y double prime is minus 1/2, and of course that's going to be minus 1/2 everywhere. Y double prime. Okay? Which means, of course, it's concave downward, the second derivative. And your curvature, capital K, is 1/2 divided by, and since your first derivative is 0 at that point, then this will be over 1, and 1 to the 3/2 power is still 1, so that would be 1/2. The curvature is 1/2. Because the curvature at the point 2, 1 is 1/2, it follows that the radius of the circle of curvature at that point is 2, which is 1 over 1/2. And so the center of curvature is at 2 minus 1, which is where I drew it, but I didn't say that, because the radius is 2 from here, 2 from here, 2 from here, 2 from here. So there's the radius, and there's the curvature. The circle of curvature inside this parabola that goes like this. So there you have it. Okay? There's a sketch of it. Any questions? Okay, we just did example 6, bottom of page 860. Okay. In the figure, note that the curve has the greatest curvature at P, because that's the vertex. If you go out a ways, like over here, then that circle of curvature is much, much broader. That tangent line. Same thing here. Much bigger circle of curvature here. You go out here and you're approaching infinite radius, because the curvature is very, 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 very small. Okay. Now, that was example 6. There is a little bit of verbiage at the top of the page 861 that usually they put in the slide set, but they didn't do it in this case. But I think it's going to be summarized by this next theorem here. Basically, it says arc length and curvature are closely related to tangential and normal components of acceleration, and they continue on. So here's what we come to. If r of t, now we're going back to a vector, either in 2 space or 3 space. R of t is the position vector for some smooth curve C, meaning no points, no cusps, no discontinuities, a smooth curve C. Then the acceleration vector is given by A of t is going to be your second derivative of your displacement. This is not a vector. That's your displacement vector, position vector. This is your arc length parameter. The second derivative of that times the unit tangent vector plus k, that's your curvature, times the first derivative of your arc length parameter squared times the normal vector. Okay? And the s dt is the speed. The magnitude of is the first derivative of the goodness, I just said it twice and now I can't get it out. Arc length parameter. The arc length parameter, the first derivative of that is the speed. Okay? Second derivative would be its acceleration, you might say. And that would be in the tangential case, the first derivative of that, the speed squared times the curvature, is the coefficient of your unit normal vector. Okay. So here's example 7, which is going to use that a bit. Okay. This is bottom of page 861 if you're trying to follow in this. So find A of t and A sub n. This, by the way, is your A sub t, and this, by the way, is your A sub n. Okay? Just to get. So, let's go back and let's see. If you remember the unit tangent, the arc length parameter vector, and that's a good ways back, so I don't think I'll scroll all the way back there. But your ds dt, that's the first derivative of your arc length parameter. From back there somewhere, you'll find this is the magnitude of your r prime of t. Okay? That's magnitude. Okay? That is what your first derivative, that is your speed, first derivative of your arc length parameter. So let's do that. R prime of t. What would that be? 2i plus 2tj, is that what you said? Minus t squared k. Right? Now, what we want is its magnitude. So the magnitude of this is the square root of what? 4t squared t to the fourth. Okay? Now, that is going to be, that's your ds dt. An easy, so to speak, expression of your arc length parameter. Okay, so this is ds dt. Okay? Now, from there, let's rewrite that slightly. 4 plus 4t squared, it's an ugly 4, isn't it? Okay. Minus t to the fourth. Wait a minute. That's plus. You square the minus t squared. Okay, so that's plus t. So that's plus t to the fourth. Okay. To the 1/2 power. Because the next thing I'm going to do is take a second derivative of that. Right? Because we need that for here. There's the ds dt. We're going to square that. We're going to come back and do that later. But we need to take a second derivative. Why go through all the headaches when you just take the second derivative of this? d2s dt squared would then be what? Help me. Take the derivative of that. 1/2 4 plus 4t squared plus t to the fourth to the minus 1/2. What next? Chain rule times 8t plus 4t cubed. Okay. A little messy, but okay. So let's write this again. What I'm going to do here, this 2 is going to divide out a 2 into there, leaving 4 and 2. So my numerator, I've got 4t plus 2t cubed, and the denominator, the square root of 4 plus 4t squared plus t to the 4th. Okay. Now, this, because that's the second derivative of that, this is a sub t. That is your tangential component of your acceleration vector. And it comes straight from here. Okay? We knew what in the other problem r prime is. That r prime, the magnitude of that is exactly this, ds dt. Then take the derivative of that with respect to t, and you get that. And that's what we just did. Now, we've got part of this one, we got ds dt. So what we're going to have to do is square that. Well, that's pretty easy to do. That would be 4 plus 4t squared plus t to the 4th. That would be ds dt squared. You just square the square root and you got it. Done. Okay? So that was pretty easy. But you also have to multiply that by the curvature. Because you see, you also multiply that by curvature. Now, that's a little bit more to do. Because this formula won't do you all that much good, because this is only for plane. Okay? Y is equal to f of x. You got no 3 dimensions there. So you go back to this form. And that's sort of a real big pain in the neck, but it is doable. Okay? So you got r prime. We got to do r double prime. And then we're going to do the r prime, the cross product of those two, and then r prime magnitude cubed. Okay, so let's go back and see if we can get that done here. Well, I've got to find it again. There we go. Okay. So we've got that squared. Let's do capital K. What was capital K again? The magnitude of r prime of t crossed r double prime of t divided by the magnitude of r prime of t cubed. Okay? Rather than scrolling back, if you're in your book, just turn back a couple of pages and you get r prime cross r double prime, magnitude of that, over r prime cubed. Okay? Now, we've got the r prime. What we don't have is r double prime. So let's do that. Here's r prime. Let's now do r double prime of t. And what would that be? Help me, somebody. Someone say something. We're r double prime because we need. Okay. We've already done r prime. That goes right here. we need R double prime. So if this is R prime, what's R double prime? 2 what? Second?
2 minus 2t.
Okay. 2j. You got to put your, okay. 2j minus 2t k. Perfect. Okay? Now, what we've got to do is do a cross product of R prime and R double prime. Okay? So, let's set that up here. I, j, k, I, j. Okay, R prime is 2t minus t squared, 2 and 2t. And R double prime is 0, 2 minus 2t, 0, 2. Okay, let's do our down diagonals, and that will be okay. I'll have to come back and do that other one. Didn't want to leave it out now because I'd forget it later. That will be a minus 4t squared. Okay, I. Okay. Next down diagonal, 0. Next down diagonal, plus 4k. Okay. Up diagonals, 0, and minus a minus is plus 2t squared I. Okay, and then the next up diagonal is minus a minus, which is plus 4t j. Okay, so you combine all those and you get minus 2t squared I plus 4tj plus 4k. Okay, there's your numerator. Now we need the magnitude of that. So the magnitude of that is what? Square root of? Help me, somebody. 4t to the 4th plus 16t squared plus 16. Okay, that's your numerator. The denominator, we've already got I know it's on here somewhere. Okay, there's your R prime. The ds dt is the magnitude of that. There it is. There's ds dt, which is magnitude of that prime. When you square that, you get this. So that's your magnitude of that squared. Then multiply that by that one more time, and basically you get, so let me see if I can get all this on here. This kappa, I'm sorry, I say kappa, capital K this book uses. Okay, is your numerator is this thing, the square root of 4t to the fourth plus 16t squared plus 16. Now what I didn't do is figure out whether that is a perfect square. And it kind of looks like it is. I can factor a 2 out of that. So let me see, let's step back and do this. 2, and then you'd have the square root of t squared plus t to the fourth plus 4t squared plus 4. And is that not the perfect square of t plus 2 squared? I think it is. So let's clean this up a little bit and make it 2 times 2t squared. Okay. 2 times 2. No. Yuck. Okay. Okay. Do that again. 2 times t squared plus 2. Okay. That was, yeah, that's this thing here. You see, that's 2 times this thing, well, that happens to be the perfect square of t plus 2. T squared plus 2. So that's what that is. Your denominator, on the other hand, is that thing up there to the 3 has power. Because you multiply this, which is r prime, times r prime squared, and you get r prime cubed. So you just multiply that to the 3rd power. So this is okay. And if I'm not mistaken, this is also 2 plus t squared cubed. Okay, so the 2 plus t squared goes out, and that gives you this, which would be 2 over 2 plus t squared squared. Okay, that's your K, capital K. I put it as a kappa, but that's just old habit. Okay. All right, now putting it all together. There's your AT to your tangential component of your acceleration. Your normal component is your kappa, which is this thing, times this thing. So this would be times, and that, by the way, is 2 plus t squared squared. So these go away, so that gives your normal component of that acceleration vector to be just 2. At least that's what I see. Let's clear my scratch out of the way and see if we can verify that. Okay? Let's erase all this. Oh, they just confirmed that the dt, I just erased it. The sdt was t squared plus 2, which is what we had, and the kappa was 2 over t squared plus 2 squared, which is what we had. So your acceleration, the tangential component of that acceleration, which I just erased, was believe it or not, let's go back and print that down again. I wish I hadn't erased it now. Your ds dt, and we had this down there, which is the magnitude of your r prime of t, and we just had at the end calculated that to be t squared plus 2. Okay, it was the square root of t to the 4th plus 4, all that kind of stuff. So it came up being that. Your kappa, now capital K, we just confirmed that was 2 over t squared plus 2. And so the product of those two was 2. So your A sub n is equal to 2. The product of those two. Now, what I hadn't done, and it took me a lot longer to do, d2s dt squared, if we had just seen that earlier, that's just 2t. And that would be your A, the tangential component of your acceleration. Okay? And your normal component was 2. So that's a lot shorter than what we did, but it's using everything we did do. All right, let's clear this out of the way, and we'll watch them do it and see the places where we did a bit much. Now, what they did, they said this is the same problem we had before. They just went back to example 5 and came up with it. But you could do r prime here, just like we did. 2 plus 2i plus 2tj plus t squared minus t squared k, and do that's your r prime. Then take your square root of those components squared, and you find out that does come up as t squared plus 2. Capital K, which we had done earlier, but we just found out 2 was 2 over t squared plus 2 squared plus 2 squared. So when you square this, you get this thing squared, multiplied by that, and you just wind up with 2. So your A sub, okay, wait, they're jumping a rabbit. A sub t, take the derivative of this, which is just 2t. Okay, that's where they shortened it big time. Well, they used the thing they already had, 2t, and your A sub n was capital K, which is 2 over t squared plus 2t, t squared plus 2 squared, and multiply that by your ds dt squared, which would have been t squared plus 2t in parentheses squared. Those cancel out, and you're just left with 2. 2t squared plus 2 squared times t squared plus 2 squared is just simply 2. That's your normal component of your acceleration vector. All right, now we're ready for application. Any questions before we leave that? A lot of mess. I carried around a lot too much stuff. I could have shortened it if I had noticed that was a perfect square. Okay. So here's your application. There are as many applications in physics, engineering, dynamics that involve relationships among speed, arc length, curvature, and acceleration. One such application concerns frictional force. A moving object with mass m is in contact with a stationary object. The total force required to produce an acceleration along that given path is force is equal to mass times acceleration. What is your acceleration? That's d2s over dt squared. Okay? Well, wait. This is total acceleration. Well, what is that? This is your tangential component of that acceleration. This is the normal component. The curvature times that squared is the normal component. Okay? So that gives you back to the formula we had. A portion of this total force is supplied by the stationary object. Is called the force of friction. And that's always going to be part of the tangential component, but it depends to some extent on the normal. Okay? For example, when a car is moving at constant speed and rounding a turn, the roadway exerts a frictional force that keeps the car from sliding off the road. Okay? Otherwise, it would just keep going. This inertia would keep it going straight, and it would just skid right off the road. That's what happens when there's a nice, smooth layer of ice on it. You go to turn, and you just keep going because you skid on the ice. There's no friction to pull you into the curve. Okay? If the car is not sliding, the frictional force is perpendicular to the direction of motion. This is the curvature here. Okay? Frictional force is in that direction, and the frictional force provides what we call the centripetal force, pulling you toward the center. Okay? Has a magnitude equal to the normal component of the acceleration. The tangential component is in the direction of the motion. The normal component is perpendicular to it. So that is your normal component. Okay? The potential frictional force of a road around the curve can be increased by banking the roadway. And you'll see that on interstates a whole lot. You'll see it on some other roads, state highways or federal highways, but a lot of county-maintained roads, they don't do as good a job on that. Force of friction perpendicular to the direction of the motion. Okay? So here's example 8. A 360 kilogram go-kart, that's the mass, by the way. So let me write that down. Might as well stay down here. Okay, so this is your mass, 360 kilograms. It's driven at a speed of 60 kilometers per hour. This speed is your ds dt. Okay, 60 kilometers per hour. Now the problem here is your units. Usually we deal in meters per second. We're in kilometers per hour, so we've got some conversions to do, but we'll get around to that later. Around a circular racetrack of radius 12 meters. So there's your picture there. Okay? Now this 60 kilometers per hour should be, well, we'll leave it alone for now. That should be your tangential vector there, but they don't show that. They show a curved vector, which isn't a vector. Okay. To keep the cart from skidding off the course, what frictional force must the track surface exert on the tires? Okay. Well, the frictional force always points to the center of the curvature. Okay. Now, if we know the radius is 12 meters, we know the curvature, because that's a circular track. What is a curvature? Anyone know? It's embedded in there, but I want, there it is. There it is. If a circle has radius r, then you know the curvature for that circle is 1 over r. So the radius of our track was radius of the track is 12 meters. So your curvature is 1 over 12. The unit is per meters, but we won't worry about the units now. So there's the curvature. Okay? Now, do you recall what and we just talked about it here, the Frictional force is perpendicular to the direction of motion, has the speed, blah, blah, blah. Potential frictional force, okay. I thought they came out and said it, but I don't see it now. This is the, oh, there it is. And has a magnitude equal to the normal component of the acceleration. Okay, so let's go back a little bit further. Here's the normal component of the acceleration. Okay, there. Cap, or K, times ds dt squared. Okay. Okay, and then we'll multiply the mass times it. There's your K. We already know ds dt is 60 kilometers per hour, but that's in the wrong units. So let's take our 60. Now this is more physics than it's math, but it's math too. It's not calculus. 60 kilometers per hour. That's your ds dt. But we got to get that into units of meters per second. So here's a good little lesson in unit conversion. Okay? We got to have at least 2 and maybe 3 unit conversions here. We're trying to get to so many meters per second. So we've got to both change our kilometers to meters. That's going to be pretty easy. But we've also got to change our hours to seconds. That may take a couple of steps. Okay? Which you want to do first? Kilometers to meters or meters or hours to seconds? I really don't care. Second? Okay. Now, how do we do that? Notice I put places for 3 conversion factors. We may not need them all, but I put 2 lines for each one. The first line is for your numbers. Okay? The second line is for your units. Always put the units in their place. So we're trying to get from kilometers to meters, put the units in the place. One goes on top, one goes on the bottom. Which goes where? Kilometers or meters? One's on top, one's on the bottom. Kilometers on the bottom, meters on the top, and that way the kilometers cancel out and you're left with meters just where you want it, on top. Now you fill in the numbers. How many meters in a kilometer, or how many kilometers in a meter? 1,000 meters is 1 kilometer. Done. Okay? Now let's do the same with hours to seconds. Does anyone know that in 1 step, or do you want to do a Texas 2-step? 1. How do you do that? Put the units in their place. You got hours or seconds. One goes on top, one's on bottom. Which goes where? Say again? Hours on top. That puts seconds in the bottom. That's exactly where we want, so hours cancel out. Now you have to answer this question. How many hours in a second, or how many seconds in an hour? Now you chose it, huh? Yeah. You chose to do it this way. If you want to do seconds, or say again? Perfect. Okay, 3,600. 3,600 seconds in 1 hour. The reason I put 2 blanks there, we could have done hours to minutes and then minutes to seconds. That would have given us the same thing. Okay, so how are we going to do this? Well, I know that 2 of the zeros will cancel out here and there. Okay, they're gone. Okay, let's do the 6 into the 36. This will give us a 10 here, and this will give us a 6 down here, and 6 will go into 10. All right, that will be 5/3. Okay, so now I've got 50 divided by 3. Someone do that on a calculator. That's going to be 1. 16.67. Okay, say that again. 16.67. Okay. You know what I'm going to do? I'm going to leave it in fractional form. Okay, I'm going to leave it as 50 thirds meters per second. Now this is in meters down here, so you're okay, but what we've got to do is square that. Remember, the formula is the curvature times the speed squared. Speed was this, so we've got to square that, and it's still not going to be very pretty, is it? I was hoping it would clean up some, but it wasn't. I got to square that, so this will be 1 over, I'm going to write 12 is 2 times 2 times 3 times, and 50 is 2 times 5 times 5, but I'm going to square that over 3 squared. Okay, so this 2 times 2 will cancel one of those out, and what we're left with is 5 to the 4th over 3 cubed. So I know that's 27 in the bottom, and up top, is that 625? Okay. So if someone's got a calculator, 625 divided by 27. A little louder? 23.14. Okay, and that would be, oh, and we got to multiply that by 360. Sorry, I forgot that. 360. 333. Okay, and that would be newtons. Okay. Let's see. Whoa, look at that. They put kilogram meters per second squared. Yeah, that would be meters. I mean, that would be newtons. Okay. 8,333 kilogram meter per second squared. Yeah. All right. Well, let's see how they did it. Okay, frictional force must equal the mass times the normal component of acceleration. From the circular path, you know the curvature, just like we said, is 1 over 12. It's 1 over 12 meters. Therefore, the frictional force is mass times that, which is the normal component, which is mass times kappa times the speed squared. That's 360 times 1 over 12 times, wow, 30, or boy, they do it with big numbers here, don't they? 60,000 meters squared. What they did was 60 kilometers and made it 60,000 meters per hour, which is 3,600 seconds, and then they squared that. And they must have used a calculator. Okay, they came up with 8,333 kilogram meter per second squared, which would be newtons. Same thing we got. I think theirs was a little, they skipped a lot of steps. All right, unless noted otherwise, let C be a curve, either in plane or space, given by this position vector. R of t is x of ti plus y of tj, or is 3 space x of ti plus y of tj plus z of tk, if that's in space. Okay, where x, y, and z are twice differentiable functions of your time t, or whatever your parameter t is. Velocity vector is r prime. Okay, that's a vector, that's a vector. Speed is the magnitude of that r prime, which is exactly ds dt, which is your first derivative of your arc length parameter vector, okay, speed, ESDT. Okay, your acceleration is the second derivative of this, which would then could be broken into your a sub t, the tangential component of your acceleration, times your unit tangent vector plus your normal component of your acceleration vector times the unit normal vector. Well, this a sub t is your first derivative of your speed, which is whatever you got this to be, take a derivative of that. That's the second derivative of that. That's your acceleration tangential to the motion. Add to that, the normal component is your curvature times your speed squared. And that's times the unit normal vector. So it's really a fairly straightforward and easy way to calculate this way. Okay? Your unit tangent vector, remember this, it's in the same direction of your velocity vector, because that's tangent to the motion, but it's a unit tangent vector, so divide by the magnitude of that velocity. Well, your unit normal vector, if you get this one, take a derivative of it. That gives you the first derivative of the unit tangent vector, then divide by its magnitude. Okay? That's quite a few steps to get there, but it's doable. Components of your acceleration, your tangential component can either be a dot t. This is not a particularly user-friendly form. V dot a, that's not too hard to do, divided by magnitude of v. Or, if you know the speed, it's just the first derivative of the speed. Okay? Your unit normal vector is a dot n, which looks pretty simple, but that's not an easy thing to calculate. You have so many steps to get there. An easier form is v dot cross a. V was pretty easy to get. A was pretty easy to get. That's just the first and second derivatives of your displacement vector. Okay? Divided by magnitude of v. Or, even easier than that, if you know the magnitude of your acceleration vector, the total thing, subtract from it this thing you just calculated. Square root of that. Or, if you know the curvature, it's the curvature times the speed squared. So there's lots of different formulas to help you get there. Use the ones that fit your problem best. Okay? What's your curvature? If it's in the plane, and you have y as a function of x without worrying with vectors, y double prime, the magnitude, absolute value of y double prime over 1 plus y prime squared to 3 has power. Okay? That's when the curve is given by y as a function of x. Okay? If you are in the plane, and you're given by parametric equations, your y, you're given a vector components, your x is your x component and your y is your y component, then it's of some parameter t, then it's x prime, y double prime minus y prime, x double prime divided by the magnitude of this thing to the 3 halves power. So the 3 halves is common here. If you have parametric equations like this rather than one equation like that, you have something that looks kind of like the beginning of a difference quotient. I mean, derivative of a quotient. The quotient rule. That's what it looks like here, but it's divided by this thing to the 3 halves power. So I don't know. You just have to remember that, look it up, whatever. That's not one I store in a memory bank anywhere. Okay? Formulas for curvature in the plane or in space. And either planar space, it's your second derivative of your displacement vector if you know the arc length parameter. That's usually not an easy thing to know. So if you know just its time parameter or whatever your regular parameter is, then it's just r prime across r double prime divided by r prime, magnitude of r prime cubed. Okay? Or the other way is cross, and this is not an easy form either. You have to go through so much anguish to get to that. So the a dot that divided by that squared. This is not a particularly easy form. Okay? This one's not too bad. Now that only applies to curves in space. Okay? This would apply, well, these would apply curve in space or curve on in a plane. And then this may not be quite as easy to mess with, quite as messy to mess with because it's in a plane. Whoa, and that's the last slide. Homework exercises 12.5. Do any of the odds 3 through 7? They're all at Calc Chat. Do number 9, it's a Calc Chat. Do any of the odds 11 through 15? They're all at Calc Chat. 13's a Calc View. Do 17, it's a Calc Chat. Do either 19 or 21, they're both a Calc Chat. 21's a Calc View. Do any of the odds 23 to 27? They're all at Calc Chat. Do any of the odds 29 through 35? They're all at Calc Chat. 33's a Calc View. Do either 37 or 39? They're both at Calc Chat. Any of the odds 41 to 47? They're all at Calc Chat. 43's a Calc View. Any of the odds 49 to 53? They're all at Calc Chat. 55 or 57? They're at Calc Chat. You can look into doing 59 if you're interested. That's at Calc Chat. Should be. 61 and or 63 are both investigation type things. You can do either one of those if you wanted to. They should be at Calc Chat. 65 is a sphere and a paraboloid. That's going to be at Calc Chat. Center of curvature 67, 69, or 71. Do any one of those three. They're all at Calc Chat. Do 73, it's at Calc Chat. There's a proof of 75. If you're interested in doing that, you certainly can. Then you have a couple more problems, 77, 79, or 81. They're all at Calc Chat. And then a couple of true-false, 83 or 85. They're both at Calc Chat. And then there's Kepler's law of planetary motion. There's some problems, 87 through 93. You can do any of those. Now, that finishes Chapter 12 finally. So if you started working on your test, that's fine, but if you haven't started on it yet, this would be a good time to start. All of you got the test, right? Okay, good deal. You didn't?
Can you go through what chapters these problems are?
I'm sorry? Okay. All right. Let me get a copy of the test in front of me. Remember, go deep enough in the file. Still don't think, well, I think I'm too deep now. Oh, I'm in the wrong class. No wonder I'm not deep enough. I forgot which class this was. Okay. What's that? Can't hear you.
Are we about to start a new chapter?
Yes, for sure. Okay. I may be too deep now. I wasn't paying close enough attention. Let me see. There's 227. Oops, those are the, okay, I went just past it, I think. Yeah, okay. your page 1, okay, you got it? Okay, page 1, the first 6 are from the first part of chapter 11. We didn't do those. They're not required to do. If you want to do them as bonus, you certainly can, but I wouldn't waste or spend a lot of time on it. Your real test starts with number 7. 7, 8, 9, and 10 come from 11.6. Okay? That's the, whatever they call that. Space. Oh, what do they call that? Quadric surfaces. Quadric surfaces. That section on quadric surfaces is 11.6. 7, 8, 9, and 10 on the first page. Then, starting the second part that says test 2, but it's part of test 1, the first 2 problems are from 12.1, 3 and 4 are from 12.2, 5 and 6 are from 12.3, 7 and 8 are from 12.4, and 9 and 10, the ones we just did, are from 12.5. Okay? And I see something wrong. Number 9. A baseball is hit 3 feet above the ground at 130 feet per second. That's not feet angle bar per second. Okay, that should be per second. Sorry, I don't know how I missed that. Everybody did get a copy of it, right? And you got now what the...
What did you say about number 9?
I'm sorry?
What about number 9?
Number 9 on the last page. The baseball is hit 3 feet above the ground at 130 feet per second. That should be a PER rather than a /ER. It's just a typo. There's nothing changed there. Now it looks like that in the vector value, it looked like the V is bolded, but it's not. I don't know why that looks darker, but I think the printer problem or something. Okay. Any other questions? All right. So actually, your test starts now. So you have 1 week from today is what you shoot for. If you finish it sooner, you can turn it in sooner. You had a weekend to work on it. Now you get another weekend to work on it. But a good time to ask questions would be any time between now and next Monday. You don't have to turn it in next Monday, but you need to turn it in before we finish the next chapter. Now, if you need additional review exercises, these pretty much go, they aren't any of them at Calc View. They're all at Calc Chat. You can do either 1 or 3. They're at Calc Chat. 5's at Calc Chat. 7's at Calc Chat. 9 or 11 are at Calc Chat. 13's at Calc Chat. 15's at Calc Chat. 17's at Calc Chat. 19, 21, 23, 25, either 27 or 29, either 31 or 33, 35, either 37 or 39, 41, 43, 45, any of the odds, 47 to either 47 or 49, 51, 53, either 55 or 57, 59 or 61, 63 or 65, 67, and either 61 or 79. And then 73 is one like we just did. There is a problem-solving deal here. You don't have to do that, but if you find it interesting, you may look at that as well. Okay? And again, odd number of those exercises are at Calc Chat. All right, we're ready now to start, as you said, chapter 13. And let me get out of this and into 13.1. All right, now how are we doing time-wise? We've just gone past our hour and a half, right? A little past that. Do you want to take a quick break, or are you okay to keep going? Up to you. What you say? What's that? What's that? Keep going? Huh?
A break.
Break. Okay, let's do a quick break. All right, I'll get this set up to go as soon as we come back. I'll put this, and we'll go from current slide. Now, the last chapter that we did, vector valued functions basically was the title of it, okay? And that was good stuff, important stuff, it's useful stuff. But these two chapters, 13 and then followed by 14, to me are the whole heart and soul of Cal 3. When you get out of two-dimensional, or let's see, derivatives and integrals to partial derivatives and multiple integrals. That's what the next two chapters are talking about. So chapter 13 is functions of several variables. We're not talking necessarily about vectors anymore here. There may be some reference to it somewhere along the way, but basically we're getting back into calculus, but it's not single variable calculus, it's multiple variable calculus. So 13.1 is an introduction to functions of several variables, okay? The objectives here, to understand the notation for the function of several variables, is to get the notation down. Sketching graphs of functions of two variables, oh boy, okay, that could be fun. Sketching level curves for a function of two variables. And by the way, some of this harkens back to what we were doing in quadratic surfaces, where we're talking about level curves and things like that there. Sketch level surfaces for a function of three variables. So that's getting into it. And using computer graphics to graph a function of two variables. Now, we're not going to do too much there, but you'll at least see those. So let's at least talk about functions of several variables. We know many of the functions of a single or independent variables. Okay, we know only the functions of single independent variable. Many familiar quantities, however, are functions of two or more variables. Now, here are three examples that the world is full of. The work done by force, work is equal to force times displacement, is a function of two variables, the force and the displacement, okay? Now, if you could get those in terms of one variable, x, that would be fine, but most of the time you can't, or a lot of times you can't. The volume of a right circular cylinder would be pi r squared h. Well, now pi is a constant. That's not a variable, so don't confuse that. But the radius could vary as well as the height could vary. So that's a function of two variables, radius and height. The volume of a rectangular solid is V is equal to the length of the solid times the width of the solid times the height of the solid. Okay, that's a function of three variables. Okay? Now, if you want to hit something that really gets a little complicated, and this is not the same kind of formulas and stuff, but this is sort of real life stuff. My wife is an epidemiologist, a researcher at UAB, and when they do studies, it's very common for them to have handfuls of variables, okay? They try to narrow them down to the ones that have the greatest impact, but she studies a disease called cytomegalovirus that affects fetuses, in utero, children there, and they can develop all sorts of things. So they look at socioeconomic status. They look at birth weight. They look at I can't think of all of them, but there's just gobs and gobs of variables. That they could go into it. Possibly sexual activity, multiple partners. There's just tons of things they can look at, variables, and they try to usually sort them out. So there's that's one. Now, getting back to something maybe a little more physical, that's more of a biological type of situation. This is the time of year when we can have some pretty severe weather. A lot of times they are trying to model what's going on, and if you think about it, you have a huge atmosphere above us, huge atmosphere. So where you are in the atmosphere, what the jet stream's doing, what the shear is doing. There's just all sorts of factors that go into temperatures, pressures, moisture content. Man, you could just get handfuls and handfuls of variables, all of which are important, and they're trying to model this in a huge, huge space, okay, our entire atmosphere, okay. That, you can easily see how you can get lots and lots of variables. Independent variables. The temperature at the various heights, temperature, okay, moisture content at various height, wind speeds at various height, pressures at various height. It goes on and on and on, okay? Now, the notation for a function of two or more variables is similar to that as a function of a single variable. Here's a couple of examples. If z is your dependent variable, and it's a function of two independent variables, x and y, then you could write z, and here's just an example, x squared plus xy. Z depends on both x and y, and x and y don't depend on each other. Then this is one dependent variable depending on two independent variables. Or, even more complicated, w, the dependent variable, depending on three independent variables. X plus 2y minus 3z. Now these are fairly simple expressions here, but x, y, and z are completely independent of each other, but what w depends on all of those. So the definition of a function of two variables, this is two variable case, let D be a set of ordered pairs of real numbers. If to each ordered pair x, y in that set D, think of that as a domain, okay, there corresponds a unique real number, f of x, y, or maybe z, okay, then f is a function of x and y. That function depends on both the x and the y, completely independent of each other. The set D is called the domain of f, and the corresponding set of values for f of x, y is the range of f, the set of values that your z could take on, okay? So then z is some function of x and y. X and y are called the independent variables, z is called the dependent variable. So let's just imagine this floor is the first octant of space. Positive x this way, positive y this way, and positive z that way. So pick a point out here. Say that's 7 on x and 12 on y, or something like that, okay? Then this point up here, z, depends on where you are here and there. Over here, the z may be here. Over here, yeah. So it varies wherever you are. Those are your z's. They depend on where you are on x and y. Think of this as the Earth, and this is the atmosphere. What's the temperature up here is a function of where you are, how far you are this way and that way, or whatever, something of that nature. The independent variables are x and y. They have no dependence on each other. They're just there, but the z depends on both of them, and both of them independently. So here's where we're going to talk about those domains. Find the domain of each function, okay? Now the domain, remember, is that set of ordered pairs, okay, x and y, okay? Now, most of the time we start with the assumption that the domain is all real numbers, unless there's something that restricts that. Well, now since we're talking about a plane of ordered pairs, it's all real numbered ordered pairs unless there's some restriction. On that first one, are there any restriction on either the x or the y? Any restriction on either the x or the y? Second? x can't be 0. You're absolutely right. You nailed it. Okay? X up here could be any value in the world. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. You're going to square it. That will be fine. Well, wait, no, there is a problem. Yeah, there is a problem. We'll get to that in a minute. Okay. The other issue is, I was thinking that was a plus there. My eyes aren't focusing too well. That is a minus sign. When I got closer, I saw it was. So there is a problem here. Okay? But you nailed one. X cannot equal 0. Okay? So x equals 0. This whole y-axis here, out of play. Can't do it because x can't be 0. All along the y-axis, x is 0. So that is completely out of the picture here. But here's the other issue. Here's a radical, okay? And we know that what's inside a radical, what about it? Can't be negative. So x squared plus y squared minus 9 has to be greater than or equal to 0, right? So that means that x squared plus y squared is greater than or equal to 9. Okay? Now, what that tells me is there's a circle down here that's x squared plus y squared is equal to 9. That would go from, see, that was my x-axis, okay? X equals 0, I'm sorry, x equals 3, around to y is equal to 3. That would form a quarter of a circle, right? That entire circle, centered at the origin, and going out there and over there and over there, that entire circle, x can't be anywhere inside that circle. Okay? It can be on the edge of the circle, because it could be equal to that, but it can't be inside the circle. Okay? Your xy, because if x was 1 and y was 2, this would be 1 squared is 1 plus 2 squared is 4, that would be 5. That's not greater than 9. So you can't be anywhere inside the circle, and x can never be 0. Okay? So those are, let's see how to express that. I'll erase it all and I'll try to reproduce what I just said. Okay? Find the domain of each function. Yuck. My pen's not showing up. There we go. Okay, the domain of this function f, this may not be how the book does it, but I like to do it this way, is the set of all ordered pairs x and y such that, that's how I like to say it, x cannot be equal to 0 and x squared plus y squared is greater than or equal to 9. That's the set of ordered pairs. X can't be 0, so anywhere along the y-axis can happen, okay? And x can't be inside the circle that's a radius 3. X squared plus y squared equal 9. It can be on the edge, but not inside that circle. Now, I don't know if that's exactly how they express it, but those are the two conditions that must be met. Let's look at B. What do you notice there? Tell me something. Anything? Okay, well there's your radical again. What's inside the radical has to be, it can't be negative. So we could say that is 9 minus x squared minus y squared minus z squared has to be greater than or equal to 0. Except, what's wrong with that? What I just wrote. It can't be equal to 0 because that is also in the denominator. So this one has to be greater than 0, which another way of saying that is 9 has to be greater than x squared plus y squared plus z squared. Now what does that describe? X squared plus y squared plus z squared.
quadratic function.
Say again?
A quadratic function.
That is going to be, it's a quadratic function, but that's going to be a sphere. There are plus signs in between, all the coefficients are the same. We're talking about the sphere there. Okay? That's a sphere of radius 3. So now it's not just, okay, now we're in 3 space, okay? And remember that circle we had here? Now the circle outlines and it goes up 3 here too. And anywhere inside that ball, and this is only an eighth of the ball because there's another one there, down, 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 down. Okay, that ball can't be anywhere inside that. It can't even be on the surface of that because that would make this equal to 0. So it can't be there, anything outside of it. So how I would express that, the domain of G would be, okay, the set of all ordered triplets. Now you have 3 independent variables, x, y, and z, such that this very thing here, 9 is greater than, let me write it the other way. I sort of like to lead off with the variables. Okay, it doesn't really matter, but I sort of like that. X squared plus y squared plus z squared has to be less than I said it wrong, okay? Has to be less than 9. That means you have to be inside the circle, not outside the circle, that ball, that sphere. You have to be outside because 9 is greater than that, meaning, no, that's right. Yeah, 9 is greater than that. So that means the x squared plus y squared plus z squared has to be less than or less than that 9. So it can't be on the surface of the ball, but it has to be anything on the interior of the ball. Okay? Now that's how I would say it. Let's see how the book says it. Okay? For the A one. The function f is defined for all points x, y, such that x is not equal to 0 and x squared plus y squared is greater than or equal to 9. Okay? So they just phrase it that way. They didn't say set of ordered pairs. Both of those facts have to be true. So the domain is a set of all points lying on or outside of the circle x squared plus y squared is equal to 9, except for those points on the y-axis, which are all out of play too. So that's why they put a dotted line on the y-axis. You don't include those 2 points. They can't include anything inside here. So the y-axis is out of play and everything inside here. The surface is in play except at those 2 points, and then anything outside except along the y-axis. So that's a pictorial view of the domain of that function. Whatever you see in blue, not counting the y-axis, and the black circle except for those 2 little circles that exclude the y-axis. Okay? The B part is this one. The function is G is defined for all points x, y, z such that x squared plus y squared plus z squared has to be less than 9. Can't be less than or equal to, has to be less than 9, which means consequently the domain is a set of all the points x, y, z lying inside a sphere of radius 3 that is centered at the origin and can't be on the surface, nor can it be outside that. Okay? Functions of several variables. Yeah. Functions of several variables functions of several variables can be combined in the same ways as functions of single variables. For instance, you can form the sum, the difference, the products, or the quotients of any 2 variables as long as that quotient function is not equal to 0. So the sum or the difference of 2 functions of multiple variables would be the sum or the difference of the functions of those multiple variables. The product function of 2 functions of multiple variables would be the product of the 2 functions of the multiple variables. And the quotient function of the two or more variables would be the quotient of the functions of those two, as long as that g of xy is never equal to 0. The others, anything that works for f and g, when you add on and subtract them, it still works for f and g. But the quotient function, that g can't be 0. You cannot form the composite of two functions of several variables. You cannot form the composite. You can, however, form the composite function f composed with h of x and y, okay, where g is a function of a single variable and h is a function of two variables, okay? So you can't form the composite of two functions of several variables. You can form the composite of a single variable function with a function of multiple variables, okay? So that's one little thing. G is a function of only one variable, but h can be a function of many variables. The reason for that is h is a function of x and y. That produces a single variable. Otherwise, it wouldn't be a function if that produced multiple. So this is only a single variable, z or whatever it happens to be, then g is a function of a single variable function. And you can form that composite, okay? Trying to think when that's ever important, but it's true, for sure it's true. I'm sure there's times when it's important. A function that can be written as a sum of functions of the form c, where c is some constant, x is the variable, raised to the nth power, y variable raised to the nth power, where c is any real number in the world, and m and n are non-negative integers, okay? They can't be fractions, they can't be decimals, and they can't be negative, okay? Non-negative integers, okay? That's the exponent. This is called a polynomial function of two variables, okay? For instance, that's for example and for instance put together. For instance, okay? The function f of x and y is x squared, that's a polynomial function, plus y squared, there's a polynomial function, minus 2xy, that's polynomial, plus x plus 2, okay? And g of xy would be 3xy squared plus x minus 2. Now, can these two functions be combined by addition? Sure. It would just be x squared plus y squared minus 2xy plus 3x squared y plus 2x plus 0, okay? So you could combine those by addition, by subtraction, by multiplication, or by division, as long as this one's never equal to 0, okay? So those are polynomial functions of two variables. Could you do a composite of f with g? No, you can't. F would have to be a single variable function, say of z, and g can be two variables here, and it's one product for any combination of x and y, single variable, then you can take the composite of f of that single variable. A rational function, on the other hand, is a quotient of two polynomial functions. So this one divided by that one, that would be called a rational function. Or this one divided by that one should be called a rational function. Any ratio or quotient of two polynomial functions. Similar terminology is used for functions of more than two variables. 3, 4, 7, whatever variables. All right. So, this is getting to the fun part. The graph of a function of two variables. The graph of a function of two variables is a set of all points x, y, z, for which z is some function of x and y. And x, y is in the domain of f. Okay? So again, picture the floor as your domain, only it can go into other spaces out there that we're not in this room, but that's your x, y. That's your domain of f. This graph can be interpreted geometrically as a surface in space. The z is that surface in space Now, when it's written like this, these are the two independent variables, there's the dependent variable, okay? For instance, this one here, that figure, here's your surface in space. Now, here we're limiting x to be positive between 0 and, say, a here, and y is also positive, 0 to, looks like that could be a as well, but it could be b, but y is just there. So here's your domain, this little square or rectangle down here just inside the first octet here, okay, like this room here. And your z value could be anything. At the corners, it is going to 0. This is a plane here, that's a plane there, there's a plane back there, a plane over here, and that cuts it. These are the arcs from this plane, from the back plane, and from this plane back there. Those are the arches formed. So all the surface here is a function of your x and y within that domain D. But z is the surface value. So we know that z of, if this is A0, is going to be 0. Z of AA or AB is going to be 0. Z of 0B or 0A, whatever that one is, and Z at 0, 0 are all 0 there. But then for other values, you're somewhere up here on the surface. Looks like the maximum value would probably be somewhere over there. Okay? That's just rough. Note that the graph is a surface whose projection onto the xy plane is your domain D. Okay? That's a lot like saying if you had some function here in the xy plane that started here and went like this, so y is some function of x, the domain would be, if you shone a light down here, it would be these values here. That would be domain. That would be outside of the domain. That would be outside of the domain. Same thing here. If you shone the light down on top of this, the shadow would be underneath that tint. Okay? The tint being the surface. Z is equal to some function of x and y. Does that make sense? Okay. Now, to each point xy in the domain D, there corresponds some point xyz, one and only one point xyz on the surface, and conversely, to each point xyz on the surface, there corresponds only one point xy in D. Okay? Yeah. So that's sort of a one-to-one characteristic there. So here's example 2. Consider the function given by f of xy is equal to square root of 16 minus 4x squared minus y squared. Find the domain and also the range of that function. So domain, how do we get that? Did we just lose somebody? Yeah, I guess. Did he ever come back from the break? Oh, okay. I hadn't paid attention, sorry. Okay. It's up to him. What's the domain of that function? Tell me something about it. Say again?
It can't be 0.
Can't be 0? What can't be 0? Okay, no, that thing could be 0. What can it?
Oh, it can't be
Ah, what's inside there can't be negative. Okay, so we know that 16 minus 4x squared minus y squared has to be greater than or equal to 0. It could be 0, but it can't be negative. Okay, and another way to express that would be 16 is greater than or equal to 4x squared minus, plus y squared. Or if you want to flip that around, 4x squared plus y squared has to be less than or equal to 16. Now, what is that describing for you there? A what? A ring? Is that what you said?
Oh, never mind.
No, you may be right. Is that what you said?
I said domain, but I don't
Domain, oh yeah, yeah. That is describing the domain. But what is the shape of that domain? What can you tell me about it? That's an ellipse. You're absolutely right. If you were to divide everything by 16, then you could express this as x squared over 4 plus y squared over 16 is less than or equal to 1. And that is an ellipse. And the major axis, another way to express this, is x squared over 2 squared plus y squared over 4 squared is equal to 1. So this is an ellipse. The major axis is the y-axis. It goes out to 4. And the minor axis is the x-axis. It's plus or minus 2. But because of the squares here, this could be plus or minus. So if we did it here on this graph, the y can go from plus or minus 4. X is plus or minus 2, that would be an ellipse, like that. Sort of that egg-shaped type thing there, but it's on the XY plane. Okay? So find the domain. How about the range of the function? Oh, I didn't write mine. The book doesn't do this, but I like to do it this way. Set of all ordered pairs x, y, such that this thing right here, and you can write any one of those forms that you wanted to. I think the simplest one would be this one, 4x squared plus y squared is less than or equal to 16. So in other words, inside that ellipse that goes from plus or minus 4 on the y-axis, plus or minus 2 on the x-axis, anywhere in that ellipse. Okay? Now, what's the range of the function? Here, oh, we haven't talked about range yet. Here's a hint. This is your z, right? That defines your range. And guess what? Radical means principal square root, positive square root. So this cannot be negative. You'd have to have a minus sign in front of that to have the negative value. So it's number 1's got to be greater than or equal to 0. That would be okay. Okay. Now, does it have a top to it? Well, we just described this as an ellipse. And if you took that ellipse and, let's see, since 16 always is greater than or equal to that, if the x's and the y's were both zeros, what's going to be the maximum?
16.
Say again?
If the x and y were both zeros.
Yeah, if both of those are 0, then the maximum this will ever be is
16.
that would be 16 square root of 16 is 4 personal. So it's going to be between 0 and 4. Can't ever be negative, and I don't think it'll ever be able to be greater than 4. So the z, the range of z, range of f, would be the set of all z's such that 0 is less than or equal to z is less than or equal to 4. Only positive because it's principal square root, and the maximum will ever be is 4. Okay? Now, describe the graph of f. Okay? Okay. I'm not good at this, so let me.
So you plug in the address.
That's supposed to be a coordinate. What did you say?
I said plug in values.
Yeah, you can do that. This is your x, this is your y, and this is your z. Okay, and you can come out x, 2, or back in negative x, negative 2. You can come out y, 4, or negative y, negative 4. This is going to be the ellipse that we were talking about. Okay, now, you can plug in values, and anywhere that you're on this ellipse, then your value is 0, and then it could come up to 4. So I'm guessing, this is just a guess, it would be sort of like a circle that way, because x squared plus, so this would be semicircles all in here, getting smaller as you get closer to the axes. That is your, is half of an ellipsoid is my best way of explaining it. Because if you did do this, let's say this is equal to z. Z is equal to the square root of 16 minus 4x squared minus y squared. Square both sides and you get z squared is equal to 16 minus 4x squared minus y squared, and rearrange those and you have 4x squared plus y squared plus z squared is equal to 16. That's your ellipsoid. Okay, that would be an ellipsoid, but because of that, z is equal, it can only be half of it. It can only be the top half, because when you squared both sides, you included the bottom half, which you can't. It's just going to be that. All right. Well, let's see how their much prettier graph than mine will go. So let's erase my ink, and let's first do the domain. Domain D is implied by the equation F is a set of all points x, y, such that 16 minus 4xy minus 4x squared minus y squared is greater than or equal to 0. We got that from it being underneath the radical. So that would be, so D is a set of all points lying on or inside this ellipse. There it is right there, the one we just said. Okay? Now, the range would be all the values f of x, y, such that 0 is less than, z is less than the square root of 16, which is 4. And that's exactly what we said too. Because whatever x, y you put in there, the maximum, the minimum x, y you could put in would be plus or minus 2 for x's and plus or minus 4s for the y's or anything along that, and your z would then be square root of 16, which is 4. Now, a point x, y, z on the graph of f, if and only if that's going to be true, that means z squared is, that's what we just did, square both sides. But now understand that now allows minus z's that you didn't have up above. That's the danger of squaring both sides. You introduce extraneous solutions. This one includes minus z's, this one does not. So you have to restrict yourself to only positive z's here. Okay? That would be this ellipsoid that we studied earlier, and that z is only between 0 and 4, not minus plus or minus 4, only 0 to 4 because of the original equation there. So there's your ellipsoid. Okay? If they had shown the ellipsoid, you have an axis here of 4, an axis here plus, this is just plus 4, this is minus 4 to plus 4, minus 2 to plus 2. Now that's hard to see. You can't see I can't see it anyway. There is a little bit of a shadow in there. Not much of one, but a little bit of a shadow in here that says that's the base of it right there, okay? And then this is the part that goes up the top, okay? Does that make sense? Okay. So that's example 2. Now, they do a thing in the book. They show the figure 13.3. They don't show 13.4 on the slide set. I sort of wish they did. That may make it a little easier to see, but let's move on. Now let's talk about level curves, okay? A second way to visualize a function of two variables is to use a scalar field in which the scalar z is equal to xy, f of xy, is assigned to the point xy. The scalar field can be characterized by level curves or contour lines along which this value of f of xy is constant. For example, in weather map shown here, these are called isobars. Okay? Okay? Iso meaning same. Isosceles triangle, two sides are the same. Isobars meaning the barometric pressure is the same at all points here. So this would be, and it all depends. Here's a map. You see the U.S. in the background here in the green, and the blue is the water around it, okay, including the Great Lakes. Well, this is showing, now these are in millibars. Here's the maximum you see here is 116 or 1,016 millibars. That would be the center of a high pressure area right there. Now, in high pressure areas, the wind flows in the northern hemisphere flows clockwise. So you have air flowing around here in a clockwise fashion. These other lines here indicate other isobars. This is 1,012, 1,008, 1,004. That's down here. So you have another smaller, weaker high pressure down here in the middle of the U.S. This one's up here in, what is that, maybe Saskatchewan, Canada, somewhere in there. There is your major high pressure. A minor high pressure is down here, where is that? Maybe Missouri or maybe Kansas, somewhere in there. Okay. Here's another fairly major high pressure over here off the coast of, is that Nova Scotia, I think, maybe there, or Newfoundland or somewhere there, is another really weak high pressure would be, no. This is a low pressure here because everything around it is going up. So there's another weak high pressure. But here is a minor low pressure just off British Columbia here. Can't quite make out. Yeah, that may be Victoria Island right there, Vancouver. Vancouver is on this side, Victoria is on that side. Okay? So you have one little low here. They may be getting a little rain here, but usually with high pressure areas you don't see any rain. Okay, and those are all minor highs. There is a small, weak, low pressure area right there. Okay, those are isobars. Okay, now if this was a topographic map, which obviously it is not for the U.S., these would be called isoclines, areas of equal elevation. And you could represent three-dimensional structures there. This is pressure here they're representing. You could have isotherms, equal areas of temperatures, and those would usually follow east to west. Occasionally you may have a spot in there where it's higher than others, maybe around big cities, and those call those heat islands, but those would be isotherms. You can have iso just about anything, okay? Here's that weather map again. This is isotherms here. In weather maps for each in which each level curve represents areas of equal temperature. That's what I just talked about, isotherms. And usually those pretty much follow east to west. However, you have a ridge of high temperatures here and low temperatures here, okay? And these are temperatures. Now, these are in degrees Fahrenheit. Boy, this is hard to read whether my glasses are on or not. This is 20 degrees Fahrenheit, 30, 40, 50, 60, 70, 80, 80, 90. So this must be spring or fall. This would certainly not be summertime, okay? I wouldn't think. But here is a special ridge of fairly warm temperature, a warmer one down here, so that makes sense. But you have a ridge of high temperatures through the mountains here, or part of the Great Plains. Fairly unusual for that to be the warmest, and fairly unusual for this to be the coolest. There is a low right there, okay, a cold spot right in the middle here, where it gets warmer here, but then colder again up here. And it's hard for me to read the outlook. Those are isotherms. Lines of equal temperature. Therms meaning thermal areas of temperatures. Bars meaning barometric pressure or atmospheric pressure. Okay? Here's another contour maps, commonly used to show regions on the Earth's surface in which the level curves represent the height above sea level. This type of map is called a topographic map. I think I've used that phrase already. And for instance, the mountain shown here would be right there, that dome right there. Okay. Now, if you didn't have numbers on them, and these are elevation numbers, you can hardly tell which is the peak and which is the valley. But these do have numbers on it. Here's 8,500. There's 6,600. I don't know what these are measured in. Don't know it. But there, right there, that's that dome right there. And then areas around that, you see it stretches out like this. So there's another sort of high area right over here. That's this one right back here. The one behind it, coming down here. And these are isoclines, areas of equal elevation. Now, where these are steepest, we're closest together, that means that's the steepest fall off. And obviously, it's pretty steep fall off right here. I think that is this one right here, where these are so close together, they're almost solidly black. Okay? And that's a very steep decline. This is more gradual, just a little more gradual on this side. The isoclines are a little spaced a little bit further apart. You get down into a flat area like this, and you see they get fairly far apart here. That's that valley that goes down through there. Okay. Somewhere down on this side over here, it looks like there's down in there is a lake, Lost Lake. I don't know where you lost it, but anyway, it's there. And you see these are low numbers. They're getting lower as you get down here, and these are isoclines around the lake, right at lake level. That would be the beach outline of the lake. That's all has to be an isocline, same level, otherwise the water would be spilling out of it. Seems to be another little depression over here, but the water can't get from here to there, otherwise it'd run out. Okay? So it may be a little pond over there. Does that make sense? And they don't give you enough to tell, but here's 5,000. It's 40, I can't read that. 4094, 6,600, 5,000. Yeah, that makes sense. 6,600 there, 8,500 there, 7,800 there. So whatever they were measured in meters or feet or whatever it is, those are some sort of boundary here. I don't know what boundary is. But those are isoclines. And these are called level surfaces. where you connect the dots for every one of those. See if I can figure this out. That's 66. Yeah, that's 66. I wish I had something. Oh, there's 78. So there's yeah. There's 200 between this. 66, 68, 7,000, 72, 74, 76, 78. So this is 1, 2, 3, 4, 5 in between there. And that was 200 between each one, so that would be 40 each. Whatever they're measuring, that would be your they have a name for it. I don't remember what it is. Okay. Okay. So these contour maps depict variations of z with respect to x and y by the spacing between the level curves. Much space between the level curves indicate that z is changing very slowly. There is little space means a very rapid change in height. So when they're really close together, that's an extraordinarily steep increase. Okay? Now, I'm thinking now, oh yeah, contour maps have to be elevation. Furthermore, to produce a good three-dimensional illusion in a contour map, it's important to choose C values that are evenly spaced. These are the contour interval, I think is what that stands for. The C value, contour interval. Okay. And that's what I was trying to do, figuring out what those were. So here's a hemisphere. F of x equals the square root of 64 minus x squared minus y squared. They've already done it for you, okay? They say sketch. No, they haven't quite. This is the three-dimensional drawing. You're to do it on a two-dimensional drawing. So here's 0 down here, and 1, 2, 3, 4, 5, 6, 7, and 8 is right at the point at the top. And that's the maximum you can get, 64. So this is a hemisphere, exactly half of a sphere, a ball, and that makes a circle with radius 8 and height 8 above the plane. This is a hemisphere, so it's only the top half. Your z's are only going from 0 to 8. X's and y are from minus 8 to plus 8. Okay? Now, what would that look like if you did a contour map of this? These would be concentric circles, and these circles are really close to each other because your ball is pretty steep right near the base. So these are really close to each other, and then they get further and further apart as you go up. So that would be, for each value C, the equation is a circle or a point in the xy plane. For example, when C1 is equal to 0, the level curve is, x squared plus y squared is equal to 64, so it's a circle of radius 8, and then you go in from there. So this is what I was describing. See here, the surfaces, they're really steep there, so they're close. So there's 0, 1, 2, 3, 4, 5, 6, 8. Evidently, two of them are really close together here. 0, 1 must be really close, 2, 3, 4, 5, 6, 7, 8. Yeah. And at the top, it feels a lot flatter than it did down here, if you imagine walking on it. Here's what it says. There's C is equal to 0. 1 is just inside that. There's 2, 3, 4, 5, 6, 7. C9 is just a point. Only place is elevation 8. Does that make sense? Yay or nay? All right. All right. One example of of a function with two variables used in economics is the Cobb-Douglas production formula. Frankly, I've never heard of this before. Okay, this function is used as a model to represent the numbers of units produced by varying amounts of labor and capital. So evidently, units produced, that's your dependent variable, the labor and the capital. Now, capital means how much money you put into running your show here. That would be your other independent variable. If X measures the units of labor, Y uses the units of capital, how much money you put into it, then the number of units produced is f of xy, that would be your units produced, is equal to some proportionality constant c, okay, just some constant, x raised to the a power, y to the 1 minus a power, okay, where c and a are constants, with a being somewhere between 0 and 1. Can't be 0, can't be 1. There's always a little bit that has to be here, okay? You can't have it all here. So this would be, could be as little as, say, 0.1, and that's going to go to 0.99, or even smaller, but usually it's something else, like 1 to 9, or 3 and 7, or something like that. C is some arbitrary constant. A is something between 0 and 1. Okay? Wow. Huh. They talk about it, and then they don't do anything with it. Okay, I didn't notice they skipped example 4. So let's go back one. That was example 3. Let's do example 4 here. Do we have time? I hope so. Let's try it. And by the way, you can go to larsoncalculus.com for an interactive version of this type of an example. Here is a hyperbolic paraboloid. Y, or z, is equal to y squared minus x squared. Okay? Hyperbolic paraboloid. Okay? Now that doesn't look like the form we had, but you know it is, because if you had z equals 0, this is going to be a hyperboloid. A hyperbola. If you have y is equal to 0, that's a parabola opening downward. X equals 0, that's a parabola opening upward, okay, on z. So therefore it's a hyperbolic paraboloid, okay? Now, it says sketch, and they give you how it looks here, okay? Now, I'm not about to draw that. I can't do a decent job of drawing that, especially in the small amount of time we have left. So let me just hold it up here. Sorry, people at home, you won't be able to see it. Go to larsoncalculus.com and find this example 4 in chapter 13, section 13.1. There's your hyperbolic paraboloid. The y is the major here, the x is the minor, okay? And when z is equal to a constant, what you have are hyperbole this way. And you see z is a constant, there's your x here, and the corresponding on the back are these level surfaces like that. Oh my goodness, this hurts. Okay? When you go up here above for positive z's, your hyperbole are going in the opposite direction. Here are the directions of opening toward positive x or negative x. Up here they're opening toward positive y or negative y. Okay? If you do a cross-section where z is constant, no, I just was describing that, say where x is constant, then you're cutting this way and you've got parabole opening upward. Okay? If when y is constant, those parabola are opening downward, as you see here, and as you get closer in there, okay? So that's your hyperbolic paraboloid. It says sketch a contour map of that surface, okay? Your zero here, if you can picture this, where does it intersect here? It's a point right there, and that's the only point that intersects. There is a line coming in diagonal this way, right between X and Y this way, and between, the backside. I can't hold the book, and that's why you have the two crosses there, the diagonal that way and that way. After that, as you're going up in Z, see your hyperbole are doing like this, and going down in Z, they're going like that. So when Z is increasing, you're going up here, and those are your curves there, and that goes up to C is equal to 12 there. That's the very one of the top ones it shows there. And as you're going down, it's going down, and you're seeing here -4. I'm sorry. -12 is here. As you're going further and further down, then your curves are along the x-axis. The hyperbole are there. Those are the -12 here, +12 there, along the y-axis. So you see, you do get this pattern here. I can't hold the book up any longer, but I probably wasn't supposed to be holding it that much because no, it wouldn't be 10 pounds, I hope. Okay. All right. Then they talk about the Cobb-Douglas function, which is what came next. Okay. But they don't show example 5. And I don't think we're going to have time for example 5, are we? Okay. So we'll pick up next time with example 5. And that will be, we'll probably do it on the same slide we did here and do example 5. So let me make a mark here, erase this one, and we'll start with example 5. Let me give you a few homework exercises to do in this section. Don't think you'll have much, but maybe just a little bit. I think you could do 5 or 7. I think you can, and they're both at Calc Chat. You can do any of the odds 9 through 19. They're all at Calc Chat. 9's at Calc View. You can do any of the odds 21 to 31. They're all at Calc Chat. 23's at Calc View. And you can think about doing 33. Okay? Try doing any of the odds 35 to 41. They're kind of tough to do because they're sketching surfaces, but they're all at Calc Chat. 37's at Calc View. And hold off, and we'll talk about the rest of those later. Okay? Good deal. All right, we'll pick up and go from there next time. All right. Hope to be able to start class on time next time. This time I had to go down and... No, that was my previous class. I'm sorry. Good deal. We'll see you next time.